Hey everyone, in this video we'll talk about Gibbs free energy and the spontaneity of processes. Before we delve into Gibbs free energy, let's define what a spontaneous process is. A spontaneous process occurs without any external intervention. Mainly this refers to any external energy input from outside a chemical system at a constant pressure and volume. So in the context of chemistry, a spontaneous chemical process or reaction refers to any processes that can occur by themselves without further energy input from outside a chemical system. And this is usually defined when the pressure and volume of the system are constant. Spontaneity or for any reaction to be spontaneous, it requires at least one driver of a reaction. In previous videos, we discussed what a driver of reaction is. This could be either a negative enthalpy change, which is a 𝛥𝐻 less than 0, or a positive entropy change, or 𝛥𝑆 value greater than 0. Colloquially, we refer to these two processes as favorable. So a negative enthalpy change or a positive entropy change are considered as favorable thermodynamic changes. When a process has either or both of these thermodynamic changes, it is considered as a spontaneous process. Conversely speaking, if a chemical process has an enthalpy change of greater than 0, positive, or an entropy change of less than 0, negative, then that process or reaction is considered as not spontaneous. A non-spontaneous chemical process or reaction does not mean that it cannot occur. It just means it can only occur when there's an external intervention or an energy input from outside a chemical system. We'll look at a few examples of non-spontaneous processes in a very moment. Some examples of spontaneous processes that you'll come across in chemistry include physical changes such as the melting of ice. So this is when water goes from a solid state into a liquid state. In this case, the enthalpy change is actually positive, so it's unfavorable, it is endothermic, but this process is made spontaneous because its entropy change, which refers to the disorder of water molecules, becomes positive as it transitions from a solid to a liquid state. So the water molecules become more disordered as they become liquid. The rusting of iron, which is really just the combustion of iron solid with oxygen gas to form iron oxide. So here we can have formation of iron 3 oxide, which is Fe2O3. In this process, the rusting of iron is an exothermic process with an enthalpy change of less than 0. And that is a favorable thermodynamic change that allows the reaction to be spontaneous. It has an entropy change of less than 0, which is an unfavorable quantity. And this is because you're converting some amount of oxygen gas into one compound of iron oxide, so the total disorder of the system decreases due to a reduction in the number of gas molecules. Combustion reactions mostly entail both favorable enthalpy changes and entropy changes. That is, its enthalpy change is negative, and due to the production of gases such as carbon dioxide and water above 100 degrees Celsius, the entropy change is also positive. So in most cases, combustion reactions are spontaneous at all temperatures because of its negative enthalpy change and positive entropy change, both of which are favorable thermodynamic quantities. Now, I mentioned that just because a chemical process is non-spontaneous, it does not mean it does not occur at all. Here are some examples of non-spontaneous processes. Electrolysis of water, which involves the decomposition of water, liquid, into the gaseous state of its elemental compositions, so H2 gas as well as O2 gas. This process is non-spontaneous and therefore requires a continuous input of electrical energy in order to break the bonds in water to produce hydrogen and oxygen gas respectively. A similar explanation can be applied to the freezing of water to form ice above the freezing point of water, which is 0 degrees Celsius. Above 0 degrees Celsius, a continuous amount of energy needs to be extracted from the water molecules in order to freeze water into its ice lattice structure. Photosynthesis is a complex sequence of chemical reactions that occur in plant cells to convert energy in the form of sunlight into energy-containing molecules such as glucose that can be utilized by plant cells to derive energy later on. Photosynthesis is an example where the enthalpy change is positive, endothermic, and the entropy change of the entire process is also negative, which means that the total entropy of the system decreases throughout the process of photosynthesis. However, photosynthesis is of course a process that occurs all the time in plant cells, but this is regarded as non-spontaneous because it requires the continuous input of sunlight, which is an external intervention, in order to facilitate this process to occur. So in summary, what I hope you take away from this section of the video is that a non-spontaneous process can still occur as long as there's an external intervention, mainly an external supply of energy to facilitate the process. Spontaneity of a process depends on the change in Gibbs free energy of the process. Gibbs free energy is a thermodynamic quantity that combines the enthalpy change and the entropy change of the process. It also considers the effect of temperature of the condition on the reaction's spontaneity. And this is all summarized by the equation that we will be using to calculate the 𝛥𝐺, the Gibbs free energy. So that is the ΔH value minus the temperature multiplied by the ΔS value. Sometimes this equation can be rewritten as the 𝛥𝐺0, which is the Gibbs free energy value measured at standard conditions, which is 298 Kelvin, so room temperature, and 1 atmospheric pressure, 1 atm. This is equal to the enthalpy change value measured at under standard conditions, so ΔH0 minus the temperature, which is 298 kelvins, multiplied by the ΔS0 value, which is the entropy change measured under standard conditions. The unit for Gibbs free energy is usually measured in kilojoules per mole, so this is same as the enthalpy change. What's important to note is that the temperature, like all temperature values used in chemistry, is measured in kelvins. And this must be a value greater than or equal to 0, because 0 Kelvin is regarded as the lowest possible temperature, and this is referred to as an absolute 0. So the T value in this equation, when you're using it to calculate Gibbs free energy, must be positive at all times. You should not have a T value that's negative. So for example, if your temperature is, let's say, minus 100 degrees Celsius, you need to add 273.15 kelvins to arrive at a positive temperature value of 173.15 kelvins, and then use this positive number in your calculation to calculate the Gibbs free energy. The relationship between spontaneity of a reaction and its ΔG value is outlined below. If the calculated ΔG value is negative, then the reaction or process is regarded as spontaneous, so it occurs without any external energy input or intervention. If the ΔG value is positive, then the reaction is non-spontaneous. And in the case where the ΔG value is equal to 0, the reaction is said to be at equilibrium. And this concept of equilibrium is explained and discussed in HSC chemistry, module 5, equilibrium and acid reactions. So for the remainder of this video, we'll focus on the first two scenarios where the ΔG is either negative or positive. Since temperature is one of the variables that's used to calculate Gibbs free energy, it will affect a reaction's spontaneity. For endothermic reactions, that is, when the ΔH value is positive, a reaction requires its entropy change to be also positive if it wants to be spontaneous. This is because for a spontaneous process, the ΔG value must be negative. So if the ΔH value is positive to start with, the second part of this equation must be more negative than the magnitude of the ΔH value to produce a sum, that is a ΔG value, that is negative. So the minus T ΔS value here, this must be negative if you want the ΔG for the reaction to be negative. Now we already said that the T, the temperature, must be a positive value. So if you want the negative T ΔS to be negative overall, then the ΔS value must be positive. If it was negative, then you'll have a double negative, right? A negative here and a negative in the delta S, which will give you a net positive. And that's not something you want if you want this reaction to be spontaneous. For these endothermic reactions, its spontaneity is favored if you have an increase or higher temperature. And that is because as the T value becomes higher or more positive, the entire second term here will become more negative, right? It becomes greater in its negative value. So you're subtracting a bigger number, which will allow your 𝛥𝐺 value to become more negative or more likely to be negative. Conversely, for exothermic reactions, and that is where your 𝛥𝐻 value is less than 0, the 𝛥𝑆 value, which is entropy change, can either be positive or negative. And that's because a negative enthalpy change is already a favorable thermodynamic quantity. It is already a driver of a spontaneous process. So you don't need the entropy change to be positive. In the case where the entropy change value is also favorable, so that is positive, then you will have a negative 𝛥𝐻 subtract a negative number as well. So in that case, the 𝛥𝐺 value will always be negative. So it'll always be spontaneous at any of the temperature values. However, if your 𝛥𝑆 value is not favorable, that means the 𝛥𝑆 is less than 0, it's a negative entropy change, then your second term here, because temperature is positive, will have a double negative, right? So it'll be minus T, which is positive, times by a negative 𝛥𝑆 value. So this will give you a positive number. So when you have a negative 𝛥𝐻 plus a positive number, the outcome of that can either be negative or positive. It will be negative if your 𝛥𝐻 is more negative than the second term. The 𝛥𝐺 will be positive, so non-spontaneous, if your 𝛥𝐻 value is less negative than the second term. That's why in the case where the 𝛥𝑆 is negative, the spontaneity of the reaction is favored, so it becomes more spontaneous when there's a decrease or lower temperature. When there's lower T value, temperature value, then the second term here will become less positive. The positive number, when you multiply by the 𝛥𝑆, becomes smaller. So you'll be adding a smaller number. And in the case where the 𝛥𝐻, which is negative, added to a smaller positive number, you're more likely to yield a 𝛥𝐺 value that is negative. So that will become spontaneous. This table summarizes the relationship between 𝛥𝐻, 𝛥𝑆, temperature, and spontaneity. So let's go through that all again. In the case where your enthalpy change is favorable, so it's exothermic, it is a driver of the spontaneous process, and your 𝛥𝑆 is also favorable, so positive, then your reaction will be spontaneous at all temperatures. It doesn't matter what the temperature is. However, when your 𝛥𝑆 value is not favorable, it's negative, then the reaction tends to be spontaneous at a low temperature. As for how low the temperature is, it depends on the actual reaction because different reactions will have different values for the 𝛥𝐻 and 𝛥𝑆. For endothermic chemical processes, the 𝛥𝐻 is positive, so it's unfavorable. This would be spontaneous only if the entropy change is positive, so it's favorable and the driver of the reaction. And the reaction will only be spontaneous at high temperatures. Again, this is related to the Gibbs Free Energy equation. When you have a positive enthalpy and you're minusing temperature times by 𝛥𝑆, you want the temperature to be as high as possible. So you're subtracting a larger number in order to produce a negative 𝛥𝐺 value. So high temperatures will make endothermic reactions more likely to be spontaneous. Now, in the last scenario is where both your enthalpy change and your entropy change are unfavorable. Neither of them are drivers of spontaneity. So in this case, when you're trying to calculate Gibbs free energy, your 𝛥𝐻 is positive and you're subtracting a negative number. So you have a double negative, so that means you'll be adding another positive value. In this case, it doesn't matter what your temperature is, your sum of the equation, which is your 𝛥𝐺, will always be positive. So your delta G here is always positive at all temperatures. So this reaction or process would be non-spontaneous. Now let's go through a few examples to practice using the Gibbs free energy equation. The formation of water from hydrogen and oxygen gas is spontaneous under certain temperature conditions. Use the following information for this question. So we're given the enthalpy change, minus 286 kilojoules per mole, delta S value, which is also negative, minus 164 joules per Kelvin per mole. Notice how the units for enthalpy change and entropy change are slightly different. One of them is in kilojoules per mole, and the other is in joules per mole, and also per Kelvin. So part A, calculate Gibbs free energy at 298 kelvins. So assuming that this is under 1 atmospheric pressure as well, when you're calculating this at room temperature, this is also the Gibbs free energy naught, delta G naught. So this is equal to the delta H value naught minus temperature times by the delta S value naught. So we have minus 286 minus the temperature, which is 298. Now we identify there's a slight difference between the units of delta S and delta H. The delta H is in kilojoules, while the delta S is in joules. So we need to convert either the delta S into kilojoules by dividing it by 1,000, or converting the delta H value into joules by multiplying by 1,000. So in this example, I am going to go with the first method of dividing minus 164 by 1,000 to convert it into joules per mole per Kelvin. And this gives me a value of delta G of negative 237 kilojoules per mole. The unit for Gibbs free energy here is kilojoules because I've converted the delta S value from joules to kilojoules. And the per Kelvin unit for entropy change has been negated because we've multiplied the delta S value by temperature, which has a unit of 298 kelvins. Now part B, is this reaction spontaneous at 298 kelvins? Our conclusion here will be yes, it is spontaneous, as my delta G value is negative at this particular temperature. I want to emphasize that this conclusion is only applicable at this specific temperature, because if you perform the calculation at a different temperature, you might yield a delta G value that is not negative, meaning that the reaction may not be spontaneous at a different temperature. Now, in the third part of this question, determine the temperature condition required for this reaction to be spontaneous. So we want to determine for what temperature values will the Gibbs free energy be less than 0. So the Gibbs free energy is a delta H minus the delta T times by delta S. We want it to be less than 0. Now, we need to make an assumption here, assuming that the delta H and the delta S values are the same for other temperatures, which may not be the case for this reaction. But this is just to convey an idea that you can use this equation as well to determine the temperature conditions required for spontaneity. So here we have minus 286 minus T times by minus 164, again divided by 1,000 to convert the unit into kilojoules per Kelvin per mole. So we want this to be less than 0. Now we can rearrange this. So this will be T. The two negatives will cancel out, become positive. So T times by 164 divided by 1,000 less than 286. So we will have T less than 286 divided by 0.164. And my answer is that the temperature must be less than 1,744 kelvins is the unit for this reaction to be spontaneous. Example 2. The enthalpy and entropy values of the complete combustion of ethane gas, which is C2H2, are shown. Determine whether the reaction is spontaneous at 50 degrees Celsius. So in this case, we are not calculating the standard Gibbs free energy anymore. This is just a delta G value. And this is equal to minus 1,300 for the enthalpy change. For this example, I am going to multiply this by 1,000 to convert the unit into joules per mole. And I'll subtract the temperature, which is 50 degrees Celsius, but keep in mind that we need to add 273.15 convert into kelvins before I can substitute this into the equation. So I'll write 50 plus 273.15, and I'll multiply this by minus 216 for the entropy change. this yields a value of minus 1.23 times 10 to the power of 6. In this case, it will be joules per mole for the Gibbs free energy. You can simplify this by dividing by 1,000, which will be minus 1.23 times 10 to the power of 3 kilojoules per mole. So since the Gibbs free energy value at this temperature is again negative, the reaction is again spontaneous. Determine the temperature requirement for the reaction to be spontaneous. Again, we have the delta H minus T times by the delta S value needs to be less than 0 for it to be spontaneous. So minus 1300 times by 1000 minus T times by minus 216 less than 0. So we have 216T less than 1300 times by 0. T is less than 1.3 million divided by 216. Here, the temperature will be less than 6019 kelvins. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.